All right, welcome again to our lessons on polynomials, our unit on polynomials. We're going to be looking today at lesson 3, which is how to graph a polynomial function. So let's go ahead and get started and see what that's going to look like. So a little bit of a reminder from the last lesson. The zeros of a polynomial function are also the x-intercepts of that polynomial. Remember that the x-intercepts is where intercepts are where the graph crosses the x-axis. When your function is in factored form, we can easily see the zeros, as we remember from the previous lesson. If you were to be given a polynomial function like this, x minus 2 times x plus 1 times 2x minus 1, you might note that this will end up being a cubic function because it's going to end up being x times x times x, or 2x. And what we can find are the zeros are 2, -1, and 1/2. And if we were to plot these intercepts on our graph, that doesn't really tell us a whole lot. And if we go to plot these out here, we say, okay, here's x is -1, here's an x-intercept. If we were to plug in x equals 2, that's our x-intercept. And if we went to 1/2, that's our x-intercepts. But we know that when we graph a polynomial or any type of function, there needs to be some sort of line going on. And we can't just connect those 3 dots because that doesn't create the correct line. So there's other things that we need to add on to today's lesson that are going to help us graph these polynomials. So the first of 3 or 4 different things we're going to talk about today is the end behavior. End behavior describes what a graph does on the left and right of the graph. So when we go and graph some sort of polynomial, we want to know what's happening out here on the right side and out here on the left side. And that actually does help us figure out what the entire graph looks like. In more technical terms, this is asking where is y going? What is happening to the y values as x goes towards infinity? If we think about a simple linear function and a linear function doing this, we're asking, okay, as x goes to infinity, so as x is getting really, really big out here, the y values are also going to infinity. In this direction, as x goes to negative infinity, y is also going to negative infinity. It's going down as x gets smaller and smaller. So we know linears, we know quadratics. We know quadratics are going to look like either this or this. And we know linear functions are going to look either like this or like this, with positive slopes or negative slopes, depending. And part of that actually depends on something that's coming up a little bit later. The end behavior is fully dependent on the degree of the polynomial. So there's 2 different types of degrees. We have either an even degree, like 2, 4, 6, or 8, or we have an odd degree, and they both do something slightly different. So for an even degree, like a quadratic or like a quartic, the end behavior goes in the same direction, and we just pointed that out for like a quadratic. And so if the leading coefficient, so let me remind us what a leading coefficient is. If we have 2x squared minus 3x plus 1, the leading coefficient is the coefficient in front of the biggest x. So in this case, the leading coefficient is 2. It's a positive number. And we know that if a positive quadratic is going to go like this. And that's what we wanted to look at. If we have a positive even degree, our end behavior both go up. We don't care what's happening in the middle because each different type of polynomial does different things in the middle. We care about end behavior. So for an even degree with a positive leading coefficient, the end behavior is going to be like this. And that makes sense when we look at a positive quadratic. Well, you might guess that if you have a negative leading coefficient, they still have to go in the same direction because it's an even degree. But in this case, they're both going down in the opposite direction. And we should know that again from a negative quadratic. Negative quadratic functions look like a U down. They go this direction. Both sides go down forever. All right, so that's an even degree, and it doesn't matter the degree. We know that if it's even, for positive leading coefficient it does this, and for negative it does this. So if we were to look at the odd degree, being 1, 3, 5, 7, 9, those type of numbers, odd degree has an end behavior that goes in opposite directions. And if we were to look at a positive leading coefficient, positive leading coefficients do this. They go down on the left and they go up on the right. And we should again know that from a positive linear function. Positive linear functions go up from left to right. And then likewise, we should know that a negative goes down. So when we go to look at the leading coefficient that is negative, the negative leading coefficient tells us to go in the opposite directions as the positive. So a negative is going to do this and this on either side. So it's going to go up on the left and down on the right. Now this seems like a silly little piece that we need to connect in here, but it actually is very, very important when we try to graph a full polynomial function that we're going to get to a little bit later in this video. All right, so the next thing. We discussed multiplicity in the previous lesson. Multiplicity being the number of times a zero occurs. So it plays a very large effect on what the graph is going to look like. So if the multiplicity is 1, that's a normal like x plus 1 like that. That's a single factor, right? X minus 2 or something like that. Each of these have multiplicities of 1. When they have a multiplicity of 1, what we're going to do is we're going to say that that graph goes straight through the 0. So if we have a 0 of -1 and a 0 of +2, and what we think about is it basically looks like a linear function if you get really, really close. So if we go to graph and we say, okay, here is our 0. We're not really thinking about this thing up here, but if we had a single multiplicity, it's going to go straight through that 0, kind of a straight line. And it could either go this way or it could go down. It depends on all of the other stuff combined, all of the end behavior, leading coefficient, all that kind of stuff. We're going to connect all of these pieces together in a few minutes. If the multiplicity is even, 2, 4, 6, all that kind of stuff, if we had a multiplicity of 2 like this up on top, we had x equals -1 with a multiplicity of 2, then we're going to use simple terms here. The graph bounces at that 0, and it basically looks like a basic quadratic function at that 0. So if we had a 0 out here that had an even multiplicity at that 0, it would come down here, and instead of going through the line, it's going to bounce and come back up. Or it could come from the bottom, it could come up and bounce down. All right, so that's what an even multiplicity does. And the odd multiplicity that is greater than 1 does a simple squiggle through that 0. Now this one is a little bit more challenging to graph, but not outside of what we can do. A basic cubic, by the way, as I mentioned down here, a basic cubic looks like this. The parent function for a cubic looks kind of like that. So if we were to think about a 0 that had an odd multiplicity, when we come up through here, we're going to do our best to try to do a little squiggle. And again, it could go to either direction. It could go from top to bottom or from bottom to top, depending on all of the other pieces. All right, so we've now looked at end behavior. We've looked at positive and negative leading coefficients. We've looked at multiplicity. There is another little one here that we need to talk about. The y-intercept is very important because that also helps us determine where we're going to draw our line. So a y-intercept is the same thing we've been dealing with every day for the last however long we've been doing this class. The y value, when you plug in x equals 0. So if I gave you a function like this, all you have to do is plug in 0. When you plug in 0, in this particular case, you get 6. So my y-intercept is the point 0, 6. So I would take that y-intercept and I would come up here to 6, and I'd say, okay, there's a dot at 6, which means my graph has to go through that dot. And then if we think about all of the other things, if I have an x-intercept here, and an x-intercept here, and an x-intercept here, and we have some sort of end behavior going on, then there's a way that we can connect all of our dots and create a sketch of a factored polynomial of any size. So we're going to put this all together now. We're going to look at this function first, this f of x up here, x minus 1 times x minus 3 times x plus 2. And we're going to we're going to find the degree and the sign of the leading coefficient. So in this case, the degree, we need to look at how many factors are there. There are going to be 3 zeros, so my degree is actually 3. You can really just count how many zeros are going to be, but you can also think that this is going to be x times x times x, which makes x cubed. And in that same sense, it's 1x, it's a positive 1x, a positive 1x, and a positive 1x, which means my leading coefficient is going to be positive. All right, so if my degree is 3 and my leading coefficient is positive, we know our end behavior has to do something like this. This is the fact that it's an odd degree and a positive leading coefficient. Then we're going to find our zeros, and we're going to plot those zeros. So we get x equals 1 and 3 and negative 2. So we have simple zeros. X equals negative 2, x equals positive 1, and x equals positive 3. Now before I do anything with end behavior here, actually no, I'm going to actually put it on there. I'm just going to put it really lightly. We know that it has to go down over here, and it has to go up over here. We're not going to necessarily use those parts as my graph, but we might be able to do that. We need to find the y-intercept. Well, the y-intercept is when we plug in x equals 0. And when we plug in x equals 0, we get negative 1 times negative 3 times positive 2. As we mentioned from the last equation, this is a positive 6. So I need to go up to 6. 1, 2, 3, 4, 5, and 6. We need to plot that y-intercept. I forgot to say this, but I wrote it up here. We said find the zeros, remember multiplicity. All of these multiplicities are 1, so there's no bouncing in this particular case. We wanted to start with something simple. we're going to connect the dots and use the end behavior all at the same time now. So we do our absolute best to draw something here. We know it has to be down here on the left, so it has to come up here. It has to go through this x-intercept. And then we know that it has to come up here. The next red dot that it finds is going to be a y-intercept. And then it has to come back down and connect to this x-intercept. And the only way to end up here in the top right is to go back up and through the other x-intercept. So here we go. We're going to do our best to draw a simple cubic function with 3 zeros and a y-intercept of 6. And there we go. We now have a simple cubic function. Our 3 zeros, as we mentioned, are -2, +1, and +3 with a y-intercept of 6. We have the correct end behavior. We have the correct zeros. We have the correct y-intercept. That is a sketch of this function f of x. Now, for right now, all of our functions are going to be factored for us because we don't know how to factor them yet. We don't know how to factor complex ones yet, and we will later in this unit. So let's take a couple looks at, or take a look at a couple other simple examples, or simple-ish examples. All right, so we need to figure out the degree. The degree is, like I mentioned, as simple as counting the number of zeros. Here I have x, but I have 2 of them. So I actually have 2 x's here, and I have 3 x's on the other one. So my degree is a 5. So we know that's odd. My leading coefficient is positive because it's x. X to the second power and x to the third power, and everything in there for the x's are positive. So my leading coefficient is positive. And since it's a degree 5 with a positive leading coefficient, I know again it's going to look kind of like the same thing as we did in the last problem. For my zeros, it's x equals -2. But in this particular case, we have a multiplicity of 2. Remember, that means it's going to bounce, so we might make a note of that. So it's going to bounce. We also have the 0 of x equals 1 with a multiplicity of 3. And we know that that's going to be a squiggle. All right, what else do we need to find? We found degree, we found leading coefficient, we found the zeros, and we made a note of the multiplicity. The last thing we need to figure out is the y-intercept. And if we do a little scratch work up here at the top, when we plug in x equals 0, we get 2 to the second power. And here we get 0 minus 1, which is -1 to the third power. 2 to the second is 4. -1 to the third is -1. So we get a -4. So my y-intercept is 0, -4. All right, so let's take a look and graph this polynomial, this quintic, right? This is a 5th degree polynomial. All right, so we need to go out to x equals 1 and x equals -2. So 1, -1, -2. We need to go down to -4. 1, 2, 3, 4. And so here we have 1, here we have -4, here we have -2. And what else do we need? We need to mention the end behavior. So we know the end behavior has to come down here like this and end up here like this. All right, so let's take a look and sketch what we know. We know that a -2 is one of our zeros, and a +1 is one of our zeros, and y equals negative 4 is our y-intercept. All right, so we know it has to end up here in quadrant 1 and it has to start down here in quadrant 4. Now, when we go up here like this, if we were to cross over at negative 2, there's no way to get back to negative 4. So that's why we say this is going to bounce at negative 2. It's going to come down here. It's going to cross at negative 4, and then it's going to come up here, and we're going to do our best to draw a little squiggle through that other x-intercept. And I think we have it. We have the bounce at negative 2, we have the squiggle at positive 1, we have the y-intercept at negative 4, and we have the correct end behavior. So as long as you pay attention to all of the pieces, this will go very smoothly. So I have one more example to get us moving. To finish us off, we have g of x. There's a reason for this particular one. So we have a degree. Here we have 2 of them, and here we have 2 more, so the degree is 4, so that's even. And then the leading coefficient in this particular case is going to be x squared and x squared, so that's positive, but this negative out in front means it's negative. So for a negative degree 4 polynomial, it's going to go down and down. And then our zeros are negative 3. Oops, not sure why I put that parentheses there. Negative 3 mult 2 and 2 multiplicity 2. So both of these are going to, oops, that did not mean to happen. There we go. Both of them are going to bounce. So that should be pretty interesting. And when we also find our y-intercept, we need to plug in x equals 0, so we get negative 3 squared and a negative 2 squared. So we get the negative that's in the front, plug in x equals 0, we get 3 squared and negative 2 squared. So we get negative times 9 times a positive 4, so we get a negative 36. It's a big number, but it's not something we can't do. All right, so here we go. We have all of our pieces, and we're going to graph those pieces. So we need to go out to positive 2, back to negative 3. Now we're going to call this right here negative 36. Oops. All right, so here is 2. Here's negative 3. Here's negative 36. Now we're going to plot everything that we know. We know we have a 0 at negative 3, a 0 at 2, and a y-intercept of negative 36. We know our end behavior goes down and down on both sides. So here goes nothing. So we know that we're going to bounce at negative 3. We're going to come down here. We're going to go through the y-intercept. We're going to come up here and we're going to bounce at the the positive 2. And we're going to go down in both directions. Now, there we go. We have the correct end behavior. We have the correct zeros. We have the correct y-intercept. Please do your best to draw smooth curves. There should be no corners. There's no sharp corners like this. Everything is a smooth turn. And make sure you make a note of all of these pieces that we need to take note of. So I am going to leave you with this, and in our next lesson that's coming up, we're going to learn how to write an equation from the graph. All right, I will see you guys tomorrow.